So, if I know that everyone is, oh, guys, sorry, I can hear people, and there are people with their backs to me. So if you can, I know we're all in the middle of exercise and alternation, but this one is really important. I promise. It's one of those that if you don't get this, there's no way you're going to do the exercises, and there's no way you're going to be able to do the hackathon. And these are non-trivial concepts, unfortunately. All right. So let's get into metrics for classification. So a lot of the work that you're going to be doing. Oh, can someone turn on the other screen, please? There's a lack of a second screen. All right. Whenever you're doing classification, so whenever you're trying to distinguish between multiple classes of things, it is a lot less obvious than it is with regression to tell how well you are doing. And the reason for that is that we are relatively good in terms of intuition about regression. We can tell that, okay, I assumed that that person's height was going to be about 1.80 meters. It turned out they were 1.72 meters. We have an intuition for what that means. We have an intuition for the differences. But when we're talking about classes, I thought that these were iris flowers, and it turned out that this percentage of the time, these were this other type of flower, but this other percentage of the time, it was this other type of flower. We might hear the results from a classifier and not figure out whether that was supposed to be a good thing or a bad thing. We're much less intuitive about that, which is why we rely a lot more on metrics when we're talking about classification. So we're going to cover 4 things. Why accuracy is highly appealing but quite problematic. Something called the confusion matrix, which is going to be part of how we solve this thing. What is precision, what is recall, and when to choose between multiple algorithms. And AUC ROC, so the area under the ROC curve, which is going to be kind of a catch-all for all of this. All of these 4 concepts are non-trivial. I'm sorry, this is kind of a heavy one, but it is also a super critical one. So let's get to the first one, more fun one. So we're going to use a medical data set, a bit altered, so none of this is real data. We have some characteristics, which, to be honest, I understand nothing about. We have whether the person had a disease or not, and we had a probability that we assigned to whether that person had a disease or not, right? And for the purpose of this exercise, nothing else matters other than these two bits. We don't care about any of the features, we just care about the outcomes, so the reality, and what we said that we were predicting. Everything else, not relevant today, or here at least. The other thing I want to stress is that the approaches that we're going to talk about now are not about machine learning, they're not about data science in particular. You can be evaluating a machine learning algorithm, but you could also be analyzing a company's decision processes, or you could be analyzing a person's decisions. These approaches apply to all of that. It's not about machine learning here. It's about evaluating how well a classification system works. So let's start with accuracy. So what is accuracy? Accuracy is a really intuitive concept, right? So it's literally the number of times I got things right over the number of times that I had to make a call. So it's quite intuitive, which is why we fall back on it so many times. For day-to-day decisions, it's not too bad, but as you're going to see, it can be substantially problematic. This is something you're going to see in the industry a lot, is people asking you what your accuracy is, and you having to give an answer such as, well, before I tell you what my accuracy is, let me tell you why that doesn't matter. And that is a very frequent answer that you'll have to give. So let's say that we make an arbitrary decision that from our probabilities, everything over 50% we decided was 1. So in this case, we decided whenever the probability was over 50 that the person was sick. Whenever the probability was under 50, the person was not sick. And so we put a down arrow when we're going to predict 0. We're going to put an up arrow when we're going to predict 1. And so we get this. So we get these predictions, which just correspond to the direction of that arrow. And then we apply this, so we just say number of correct predictions over number of predictions, and we get 93%. And that actually looks good, right? 93%, it's kind of a big number. It's over 90%. That sounds good. But now let's do a very trivial exercise. Let's say we have an intuition most people are not sick. So we build this really simple classifier that says no one is ever sick. And we get a performance of 98% with this fantastic classifier that says no one is ever sick. So as you can see, accuracy is super dangerous because a trivial algorithm, or in this case just no one is ever sick, can beat the classifier by a lot. And that is because of this question of class imbalance. When the two things that you're trying to predict are not in the same amounts. So if there were 50% people who were sick, 50% of people who were not sick, this would kind of make sense. But generally, that's not true, and accuracy generally isn't a good metric. Actually, accuracy is dangerous, is what I wanted to leave you with here.
Sorry.
Yep.
For example, in this case, you could have measured the accuracy just in the group of people who are sick, for example.
So you could have done a bunch of different approaches, which would have changed the overall metric. Yeah. That's definitely true. Yeah. And we're going to touch on how to fix that. So the accuracy when deciding this, the accuracy when deciding that, that's exactly the right approach. What I'm talking about is the overall number of decisions I made correctly over a total number. But yeah, that's the right way to think about it. Okay, confusion matrix. This is where we go down the rabbit hole. The confusion matrix is quite a simple thing, but unfortunately gets us confused, no pun intended. On the top is the predictions that we made. On the horizontal is what we observed. So just that simple. There are multiple nomenclatures for this, but fundamentally it's always the same thing. If we predicted that it was positive, in this case, positive means sick. If we predicted that that person was sick and that person was sick, we get a true positive. If we predicted that they were not sick and they are not sick, it's a true negative. False positive when we predicted that they were sick, so also called false alarm. And false negative is when we said they are healthy and they turned out to be sick, right? So this is the confusion matrix. And this is now where we're going to get exactly into what you're mentioning. For kind of a memory thing, true and false are whether we were correct or not. And then positive and negative is the prediction that we made. Don't worry about memorizing this yet. It will be, all of this is in the learning notebooks. The important thing is to get the intuition that we are going to use this thing to make decisions. So if we go back to our sickness predictions, so we have the situations where we predicted 1, the situations where we predicted 0, and we can go and see what our true positives, true negatives, false positives, and false negatives were. So in this case, we got this particular confusion matrix, and we can start trying to interpret a few things, right? So if we look at the people who were healthy, and correct me if I get this confused, because even after 5 years of this, I still get these every once in a while wrong. Of the people who were healthy, we always predicted that they were healthy. That's how to interpret that sentence, right? And these are the statements that are way more useful than just saying 93% or 98%. Okay, confusion matrix, second row. Can anyone give me the answer to this one? Instructors included.
People who were sick, we predicted 19, we got it wrong 19 times?
Yes. Of the people that were sick, bravo. We got them almost 20% of the times wrong because we got it wrong 19%. Which, if we think about it from a medical application, it's kind of problematic, right? We'll get into that. Okay, now vertically, who can interpret this one?
Of all the times we predicted the person was sick, was not sick, we were right 290 times.
Excellent. Of the times that we predicted that they were healthy, we were correct 219, but wrong 19 times. And last one, does anyone want to hit me with the last one?
From every time we predicted that someone was sick, the world was wrong. Actually, we never.
Every time we predicted someone was sick, they actually turned out to be sick. Perfect. So the question, if we have this application for, let's say, a medical device or for predicting triage, we've got an algorithm with 93% accuracy. Can we go home now? Here's our confusion matrix. Is this okay? No. We already established that our trade-offs are terrible, right? So we've developed something that just, when people actually are sick, it actually messes up 20% of the time. I don't really care whether you've got 93% accuracy. When it matters, this thing is actually quite terrible. This is where lots and lots of data scientists who are in the industry completely mess up. They look at an overall number and don't interpret the circumstances in which this is going to be used. Super, super important thing. This leads us to precision and recall, which are just transformations of what we just said.
But sorry,
Mhm.
maybe a good algorithm or a bad algorithm, depending on your problem. Maybe it's a good one. It depends.
Exactly. We're absolutely going to get into that. It's entirely dependent on what type of problem you do have. So for a medical application, this one's terrible. For other cases, it actually could be good. If the cost of mistaking someone sick was actually not particularly problematic, but what you wanted to avoid was sending healthy people home.
Even for a medical application, if the cost of the disease is not too bad, but the cost of performing like wrong treatment is very high.
That is absolutely fair. However, it undermines my initial premise.
Well, let's say it's like cancer diagnosis.
Yes, we're going to go with cancer diagnosis. But yeah, that is a good point. So if this were, well, the point was being made was that, oh, but if the cost of making a mistake and saying that someone healthy was sick was higher because we sent them to some treatment that they didn't need and the treatment was problematic, then that would be fine. But for argument's sake, let's say it's like just triage and we're trying to make sure that people who are sick get treated. So, okay, very simple concept here, but one that's going to trip you up a few times, which is the concept of recall. The concept of recall is of all the true positives. It's the true positives divided by the sum of the true positives and the false negatives. The one thing that I want you to remember from recall is not this, because you can always look this up, is only this, that if I don't have enough recall, I will send sick people home by mistake. Okay? That's the bit that you want to remember from all this. Recall is when I'd rather be wrong by sending some people over to be examined by a doctor than being wrong by sending sick people home. The reverse of that, and actually touching a bit upon this question of, okay, but what's the counterexample to that, is the idea of precision. And again, precision can be thought of, okay, true positives plus false positives. You'll have these in the exercise. You'll get the intuition for it as you get it wrong over and over again, as I did for years. But the point here is, in this case, you have a precision of 1. Of the people who are actually 1, we always said that of the times that we predicted 1, they were always 1. And the good example here would be a judge, right? So a judge should not send people to prison when they are innocent. It is better for them to send a few people who were guilty but couldn't quite be proven guilty home instead. So recall is the doctor, precision is the judge. The recall cares a lot about false negatives, the judge cares a lot about false positives. Obviously, with all the caveats that are in the middle, but when you need to remember which is which, it's easy to think of these two. So let's take these two. So I'm actually going to ask you, in a medical application, which one is best, and in a legal application, which one is best, and why? Instructors included again.
Medical recall and the legal precision.
But my question is about, that is true. However, my question is, which one of these two classifiers, which has these properties of false positives, true positives, false negatives, true negatives, would you choose for a medical application? They both suck, right? So they both got big trade-offs. That's the point.
So the left one is better for law stuff, going on the right for medical.
And why? So the point.
Well, if we just look at the left one, true label 1 means, for example, a person is sick, and I predicted that he's not. It's 168 people that we're seeing that are sick, so that's bad.
Perfect. Yes, that is the correct answer. So on the left side, we have of the times that they were, let's go with medical application first to show that this makes sense. Of the times that they were sick, we sent them home a huge percentage of times. Whether if it's a legal application, of the times that they were guilty, we actually missed a few. Of reversing that, also on the left side, of the times that they were healthy, we sent most of them to home, but we sent a few through. Of the times that they were innocent, we mostly sent, but sent still a few. Now the really tricky one is the one on the right, right? So the right one is quite a weak algorithm. So when they were 0, it actually sends lots of people to 1, right? So it's got a huge number of mistakes on that upper right corner. So we have to make the call of where would that be least problematic, if it's sending lots of people to triage or sending lots of innocent people to jail. The reason why I'm making such a big fuss about this is because unfortunately this is something that the industry very, very often fails to take into account. And you will face lots of pressures as data scientists often from business, to come up with a really clear and obvious justification for why one model is better than the other. And it will fundamentally be your ownership to decide this is the model that should be put into production, not that one. And it won't be because one model is really good and the other model is really bad. That is really, really easy. Your job will be, and you'll pardon the swear words, to choose between a shit sandwich and a shit kebab. And at that point, you'll have to choose the one that does less damage in the real world, and that will be making these kind of really tricky decisions. All right, so the dream would be to find like a sweet spot, right? And this is where you'll find some people coming up with this argument that, well, actually, you can have like a thing that does an average between how good your precision and recall are, and you'd come up with a single metric, and you could just maximize on that. And that is called the F1 score. You'll run into this a lot. I will make the point here that the F1 score should come with all of these labels, because the F1 score assumes that the cost of a false positive and the cost of a false negative are the same. And that is an assumption that I have never seen hold up in the real world. So F1 score generally comes prefaced with, you know, actually, but it doesn't really work. All right, last concept. Let's start with a really simple thing. Let's say that we have a bunch of outcomes and some probabilities that we predicted, right? So before, in the first bit, I just said anything that's over 50% probability is 1, anything that's under 50% probability is 0. But that's obviously too crass. That doesn't make any sense. So here we would get 1 false negative, but if we predict increased threshold to 0.8, we'd get a different combination of false negatives and false positives. If you try another thresholds where we say, okay, anything over 0.1 is 1, anything over under 0.1 is 0, then we get another trade-off. Does this make sense to everyone? So as we move that threshold, we start getting different trade-offs of true positives and false positives and false negatives. So what I want to remember from this is that it's kind of hard to catch more true positives without catching some false positives. Make sense? To get one, you need to compensate on the other. So graphically, we can do one thing, which is just plot the false positive rate versus the true positive rate. And just, okay, as we are going along the threshold, we get these, then we evolve to this, and towards the end, we get all of the true positives, but we also got all the false positives because we just said 1 to everything, right? That chart makes sense. The tricky transformation here is thinking, we don't need this threshold axis. We can just plot the false positives versus the true positives in one go, right? So for each true positive value, there's only one value of false positive, so we can just do some crazy transformation that makes one against the other. So ignoring the math behind that, if we plot one versus the other, we get this, right? Which is just the true positive rate on the vertical axis, the false positive rate on the horizontal axis. You do that, and you've got what's called the receiver operator characteristic curve. Ignoring why the name is so complicated, everyone just calls it the ROC curve. Half people can't even remember what ROC stands for, but the point is this shows you how well your classifier does in general. How much optionality does this classifier even give you before you have to make decisions about where to put the threshold. The reason why this is so important is because this is generally what you end up using for model selection. More junior data scientists or people who come from industries which are quite conservative will go and set a threshold and then make a decision. However, the best way to do it is generally to look at the ROC curve because it shows you all of your potential trade-offs. So if you think about the thresholds that we were talking before, one will put you here, but the other one will put you somewhere completely different. So the trade-offs are shown all in one chart, particularly once you get used to that chart and start being able to read it better. And one natural question to have here would be, okay, but what would be the ideal ROC curve? If everything was perfect, what would it look like? And the answer is it would look like that. The moment that you started before you got your first false positives, you have caught all of your true positives, right? Before I sent a single, let me make sure I get this right. Before I send a single innocent person to jail, I've put all of the criminals in jail, and only then do I start making false positives. So that's the perfect classifier. And one caveat, if I'm doing decisions at random, I'm actually going through that diagonal. That's less important, but if I make a mistake and have to send the same proportion of innocent and guilty people to jail, then I'm following that diagonal, which is actually an advantage of the ROC curve because it doesn't depend on how many you have of each. That matters less. One really important concept is also quite a simple one, which is the area under this rock curve. So the more area you have under this rock curve, the better your classifier is. And this is actually a single metric, which is quite useful to look at. It's not a panacea, but it's much better than all of the other metrics that I mentioned before. Because if you can look at the area under the rock curve, you can kind of give you an idea of how much optionality your classifier is giving you. So choosing between two classifiers, choosing the one that has the highest rock curve in most cases is actually a decent approach. This would be the area under the rock curve of our particular classifier, of the one that we were working with. So it's 0.7. It's actually not terrible. If it's just a diagonal, it means you're flipping coins at that point. You're just making random decisions. And anything that's under the diagonal line means your classifier is worse than random, meaning it kind of is useful. It's a bit like me with directions. My girlfriend always asks if it's left or right, and if I say left, she goes right. So I'm useful in that way. And so I'm going to leave you with this not entirely true idea, but useful idea that the area under the rock curve will kind of be your holy grail, at least for the hackathon and for a few other things, because it's what you'll end up using to make decisions between multiple classifiers. All right, so very quick recap. Accuracy is dangerous. Learn how to have arguments about why you're not going to answer questions about what your accuracy is, or at least saying, I'm going to give you a number, but I'm going to caveat you by saying that this trivial classifier is better than that number. Best totally depends on the context, and this is maybe the most important point. Think of the context. You cannot be, I'm going to insult someone here, but a front-end engineer can care only about the website and the technology and the user, etc. A data scientist who is working in an algorithm needs to want to know the entire business, the premise, why that is being built, and actually has to own that decision. It's a different type of responsibility. You don't get to be a small box in a big group. You need to understand exactly why that is going to be built, how it's going to be used, who it's going to affect, and if it goes wrong, what happens. That is on you. There's no way to discard that responsibility over or to say, oh, but the CEO told me, because the CEO doesn't know what the area on the rock curve means. It is effectively your decision in the end, what classifier gets chosen. And finally, just to end with a stupid pun, the A-Rock rocks, and this is probably what you're going to be using a lot during the next few years. I've managed to make Sam cringe, so that's a big victory. So now, go evaluate some classifiers.